Hello friends, good morning. This is Professor Girish Atnikar from Department of Mechanical Engineering, Indian Institute of Technology and Management, Belgaum. I welcome you all for today's session. So in today's session we'll be having a look at a problem on torsion of shafts. In this case it would be a hollow shaft. So I have listed the problem for you. Please go through this. The statement I have just written for you. You can just go through that. Okay, and in your examination he will be just giving you the statement up to this point. Depending upon the statement you need to construct the diagram for this particular problem. The diagram will not be given to you, right? So he has given that a hollow circular shaft 2 meter long is firmly supported at each end and has an outside diameter of 80 mm. So it is supported at both the ends, it is fixed at both the ends. It has outer diameter of 80 mm and an inside diameter of 63.8 mm. That is what I have drawn. The shaft is subjected to a torque of 12 kilonewton meter at a distance of 1.5 meter from one end. So I have taken from this end it is 1.5 meter. So this is the node where 12 kilonewton meter will be acting. Right, thus you need to calculate the maximum shear stress and angle of twist in the shaft. He has given us the modulus of rigidity as 8 into 10⁴ Newton per mm square. So once if you are done with this diagram, you need to write the element diagram. You need to draw the element diagram. That is what I have drawn. So in this case there would be two elements. So from node 1 to node 2 this will be element number 1, and from node 2 to node 3 this will be element number 2. Right, so these are the two elements. Now after that, the important thing where many students go wrong is in finding out the polar moment of inertia, that is J. In a regular problem of shaft it will be pi d⁴ divided by 32, but here we should be careful because he has given us a hollow shaft. So the formula slightly changes. It will be pi into d naught. D naught is d outer diameter minus d inner diameter raised to 4 remains same divided by 32. So if you just simplify this, putting the values as 80 and 63.8 which are given in the problem, we will be getting 2.394 into 10⁶ mm. Right, so that will be the first and foremost thing which you will be doing. So thereafter we will be starting with the problem. So step number 1 is to find out individual element stiffness matrices. Yes, element stiffness matrices. So that would be your first step, to find out the individual element stiffness matrices. So you know the formula. So K1 is equal to G into J1 divided by L1, 1 minus 1 minus 1 and 1. Right, so this is the formula. So G value is given as 8 into 10⁴. So it is given in the problem, Newton per mm square. J value I have found out, it is 2.394 into 10⁶ divided by, be careful now, length of the element. Right, so length of the element you need to be careful because J is in mm⁴, G is also in mm square, whereas length is in meters. So you need to convert this 0.5 meter to mm. So it will be 500 mm. Right, length you need to put it in mm. He has given it in meter, so you be careful. So it is 1 minus 1 minus 1 1. So if you simplify this entire thing, whatever I have written here, so you will be getting K1 will be equal to 10⁶ 383.04 minus 383.04 minus 383.04 and 383.04. Right, you also write the associated angle of twists. This is θ1, θ2, θ1, θ2, so that it becomes easier for us to add these individual stiffness matrices in order to obtain the global stiffness matrix. So similarly K2, The formula will be G into J2 divided by L2, 1 minus 1 minus 1 1. G and J values are going to remain same. L value is going to change, right? So L value is 1.5 meters, so you need to substitute the value of L here in this as 1500, right? 1.5 into 1000 mm, it is 1500 mm. So if you simplify that, the outcome will be 10 raised to 6, 127.68 minus 127.68 minus 127.68 and 127.68. So that will be the final values. Once again, associated angle of twists theta 2, theta 3, theta 2 and theta 3, right? So this is theta 2. Now you know what is to be done. Once if we get the individual stiffness matrices, we just need to add them. That will be our second step. So second step is find global stiffness matrix. So how you do that? K is equal to K1 plus K2, right? So if you are going to add these K1 K2, what will be getting? 10 raised to 6, which is a common thing. We'll be getting 383.04 minus 383.04. This value will be 0 minus 383.04. This value will be 510.72 minus 127.68. This value will be 0 minus 127.68 and 127.68. So these will be the final values of the global stiffness matrix. So this is theta 1, theta 2, theta 3, theta 1, theta 2, theta 3, right? So by this time you know how to add these two individual stiffness matrices, so I need not repeat it. Next we'll be going for step number 3. We'll be going for step number 3. So step number 3, we know that K into theta is equal to torque, right? So K matrix is 10 raised to 6, so it is 383.04 minus 383.04, it is 0 minus 383.04. Then you are having 510.72 minus 127.68. This is 0. This is minus 127.68, 127.68. So that is your global stiffness matrix. Theta matrix will be theta 1, theta 2, theta 3. So this will be equal to torque. Okay, now be careful with torque. Now let us check out what are the values of torque we are knowing. So here at node number 1 there is no torque given, so T1 will be equal to 0. T3 at node number 3 no torque is given, so it will be equal to 0. At T2 at node number 2 you are having a torque which is 12 kilonewton meter. 12 kilonewton meter. Since everything is in mm, I also need to convert this meter into mm and also this kilo into newton. So what I am trying to tell here is at point number 2 torque should be written in Newton mm. So if you are going to write it in Newton mm, what we will be getting? So this particular value will be 0. Here it is 12 into 10 raised to 3 into 10 raised to 3. 1 10 raised to 3 is to convert into mm and the 10 raised to 3 is to convert kilonewton into newton, and here it is 0. Now by elimination method using boundary conditions, put theta 1 is equal to theta 3 is equal to 0. Why theta 1 is equal to theta 3 equal to 0? Because both end 1 and end 3, both the extreme ends are fixed. So the angle of twists at those extreme ends, wherever they are fixed, it will be 0. So you know what is to be done next. When these two are 0, those particular rows and those particular columns I need to strike out. So first it is theta 1. So first row and first column is striked out. Third row and third column is striked out. So the remaining thing is 510.72 into theta 2 will be equal to 12 into 10 raised to 3 into 10 raised to 3 is 10 raised to 6. So this is divided by this value, which is 10 raised to 6. So these two are going to cancel. So 510.72 into theta 2 is equal to 12. So therefore theta 2 value comes out to be 0.0234 radians. Right? Next, so once if you find theta 2, we'll go for step number 4, which is to find out shear stresses. Right? So you know what is the formula to find out shear stress. In the first element, it is G into R1 divided by L1 minus 1 1 theta 1 and theta 2. So if you substitute value, G is 8 into 10 raised to 4. Now be careful with this R1. I told you R1 is radius. So in this case you need to take radius, that is 80 divided by 2, 40 mm. 80 divided by 2, that is 40 mm. So divided by length of the element is 500. Theta 1 is 0. Theta 2 is 0.0234. Right. So if you simplify this and multiply with this matrix, you will find tau 1 to be 149 Newton per mm square. Right. Similarly, tau 2 is G into R2 divided by L1 minus 1, L2 minus 1 1. Here it will be theta 2 and theta 3. Right. Now G value is remaining same, 8 into 10 raised to 4. Once again, R value you need to take it as 40 only. Right. So R value you need to take it as 40 divided by 1500. Length of the element is 1500. Theta 2 value is 0.0234. And theta 3 value is 0. Right. So if you just simplify this part, you will be getting tau 2 as 49.92 Newton per mm square. Right, 49.92 Newton per mm square. Now we are having minus 1 here. So if you simplify this everything, you will be getting 49.92 Newton per mm square. with a negative sign, right? So if you resolve this everything according to this, you'll be getting the value as so much, right? Also, you be careful, I have missed out this -1 1. I have just written gr1 by l1 and θ1 θ2. I have missed out this one, so please add this. Same thing here, it is -1 and 1. So you simplify this, that you multiply with these two matrices, and when you do that, outcome will be -49.92, right? I repeat, I have missed out this -1 1 -1 1 in both the cases, right? No doubt your answers will be correct. So you just simplify this entire part, you will be getting 149 in the first case and -49.92 in the second case. Next, right? So that's it. The maximum stress is 149 and the angle of twist what he has asked for is 0.0234 radians, right? So that's all. That is the end of the problem. Before we could wind up with the today's session, I have something important for you which will be asked many times in many of the competitive examinations. At times these are also asked in your VTU examinations, so you should know this. Okay, now what I am talking about are the special type of elements. Okay, you have studied about one-dimensional element, two-dimensional element, three-dimensional element, or it may be simplex, complex and multiplex. Okay, those are also the types of elements which come under FEM. So these are some special types of elements, right? In that the first one is subparametric element. Subparametric element. So what does it mean? Number of nodes used to define the geometry is less than, okay, this is less than, is less than number of nodes used to define the displacements. So I have taken an element of this shape which is rectangular. Now I have two types of nodes. These red colored nodes what I have shown, these are nodes for geometry, or nodes which are used to define the geometry. And these square boxes what I have used, these are the nodes which are used to define the displacements, right? Red color nodes are nodes which are used to define the geometry, whereas the square boxes are nothing but nodes which are used to define the displacements. So if the number of nodes used to define the geometry is less than the number of nodes used to define the displacements, then such kind of element we call it as subparametric element. In short, NG, that is nodes to define the geometry, is less than the nodes used to define the displacements. Right, you can just check out. In this case, nodes to define the displacements are 6 in number, 1, 2, 3, 4, 5, 6, and nodes to define geometry are just 4, 1, 2, 3, 4. Right, so that is subparametric element. Next comes the second type, which is superparametric element. Superparametric element, here it is other way. If the number of nodes used to define the geometry is greater than the number of nodes used to define the displacement, then it is called as superparametric element. I have taken the same example once again, but here what are the changes you find is these red colored nodes, I told you these are nodes for geometry. So 1, 2, 3, 4, 5, 6. So NG is 6, and these square boxes are for displacements, it is 4. So 6 is greater than 4, or NG is greater than ND. So number of nodes used to define geometry, which is NG, is greater than the number of nodes used to define displacement, that is ND. Such examples we call them as superparametric element, right? So that was the second type. Next comes the third type, isoparametric element. In this case both are equal. Number of nodes used to define the geometry is equal to number of nodes used to define the displacement. The red colored ones are the displacements, and the red colored ones are the nodes used to define geometry, and the square boxes are the nodes used to define the displacement. I have taken the same example in each and every case in order to avoid the confusion. So here ng is also equal to 4 and nd is also equal to 4. When both are equal, we call those elements as isoparametric elements. Right? The next type, serendipity elements. Right? These are rectangular elements with no internal nodes, or you can call them as zero internal nodes. I have taken two examples, both are rectangular. In both you can see that within the element, that is in this space, there are no internal nodes. So any rectangular element which is not having internal nodes, it comes under the category of serendipity elements. And the last type, which is Lagrange elements. So these are the rectangular elements with internal nodes. Right? So we are having two rectangular elements. In both cases, you can just check out here, there is one internal node, here there are two internal nodes. So if the internal nodes are present inside the rectangular element, then it becomes Lagrange element. If no internal nodes are present inside the rectangular element, it becomes a serendipity element. Right? So these are 5 important types of special kind of elements which we'll be using in our FEM. Right? So that's it for today's session. Thank you. Please subscribe my channel. Do share it with your friends. Have a good day.